Well, there was a new option this time, enable smart recording with AI something or other. So interesting. Maybe I should try that and see if that will learn how I set up my windows and I can just hit one key and it'll get everything set up for me. Um, all right, so the plan for today is to finish 3.9 related rates, one and a half or so problems to finish there, and cover 310 linear approximations of differentials. So unfortunately, I wasn't feeling well last Wednesday. I posted a post to Blackboard, um, and it's supposed to copy it to your email, but I actually checked my email just today because somebody had asked about it, and um, I don't know if I got a copy to my email, so that's kind of unusual. I don't know if I deleted it or put it in a folder that I can't find it now, but I didn't see one come to my email. But I think I posted it on Blackboard and it should have been available for you. But if you ever, go to log on and, um, it doesn't seem like things are starting up, check your email, check Blackboard. And if I ever do have to cancel a class, hopefully I won't have to cancel another one this semester, but I'll post something there. Um, so the makeup video to be posted is on 311 hyperbolic functions, which comes right after 310. Um, Yes, this is a math course, even though 3.10 comes after 3.9. Sorry about that. Um, so um, the video is currently editing on YouTube. For whatever reason, when I edit videos on YouTube, it can sometimes take up to even more than a day for it to finish editing. Like uploading is really fast. So usually when I upload, it kind of does all the stuff that it needs to do with processing it and checking it for copyright issues and all of that kind of stuff. Um, but then for whatever reason, if I like try to edit the video, it takes it a really, really long time. Maybe I just need more likes and subscribes and, more YouTube cred or something for it to go faster. But so I'm hoping it'll be available this afternoon. But whenever it's done processing, I'll make it available and it'll be in the same playlist as all of our class recordings. So 311 hyperbolic functions, pretty short recording. I want to say maybe a half an hour, 40 minutes or something. Um, and then kind of the part two of the makeup material is related to the midterm exam coming up next week. So studying for that, working through the sample exam and so on. But just a reminder, the Examity practice exam is now available. So if you haven't had a chance to take that, I would strongly recommend in the next day or two getting into there. There's a Blackboard post with lots more information on it, but basically go into Blackboard, click the Examity sign-on link, log into Examity, create an account if you need to. You might not need to if you've done it for another course, but get everything set up on that end of things and then do the Examity practice exam that's on WebAssign. Again, that exam is not meant, it doesn't count for your course grade. It's not meant to assess your readiness for the material or anything like that. There's a few dummy questions in there, but really the purpose is for you to go through once, starting up Examity, getting into an exam, making sure the password widget works, closing out the exam and the Examity session and all of that. So that you've gone through it once before exam day. And so you can make sure all the tech is working and all that on the front end before we get to exam week. Midterm exam week is next week. So this coming week or next week, depending on how you want to describe it, the week starting a week from today. The midterm exam will be available from 9 a.m. on Monday the 21st through 11:59 p.m. on Sunday the 27th. The material is probably going to be chapter 2 and 3.1 through 3.9. I haven't completely made the exam yet, so this could change a little bit. I might take 3.9 off of there. I might leave 3.9 on there. That's probably about as much as it would change. So, I'll post an announcement with all of the final details and later this week in a couple of days or so. And also the sample exam will be posted in the next couple of days or so. So that will be posted after I've kind of finalized my the actual exam and know exactly what material is going to be on there. So all of that should give you a really good idea of what's going to be on the exam. And you can go through the sample exam And I usually recommend treating it like an actual exam. Sit down, give yourself the amount of time on the actual exam. It'll probably be 2 hours, but again, that might go up or down, or well, won't go up, but could go down if you know, if I end up putting fewer problems on it or fewer sections on it. But sit down, give yourself the same amount of exam time as the actual exam. Um, Set yourself up in the same environment and take the sample exam as if you were taking the actual exam. And then you can look back and you can say, okay, was the score I got in the sample exam, would I be happy with that if it was the actual exam? Were there any problems I struggled on? Was there anything that felt like it took a lot more time than it should have? And if so, that might give you some direction to study for the exam. So that's kind of the other half of the, quote, makeup material is to take some time and do that. So reviewing the sample exam, definitely a good idea before the actual exam. And if you go through the sample exam and you're happy with your score, then you're probably, going to be happy with your actual exam score. And if you go through the sample exam and you identify a couple weaknesses, you work through some past homework problems or some, third-party study materials or something, feel like you get a better grasp of it, you can take the sample exam again and see if your score improved. I think it should be set up so that when you take it again, it re-randomizes things. Um, so in the distant past, I had it set up that way. In the recent past, some students asked me to set the exam up a slightly different way. Um, so I did, but it turned out that more students disliked that than liked it. So this semester I'm switching back to the old way of doing it. So you should be able to get a re-randomization in the sample exam. I think that should work. If it doesn't work, let me know and I'll make sure that the settings are set correctly. And then also you can use a formula sheet, front and back of a standard size sheet of paper. You can have, formulas or notes, anything like that you want on it. You can use a calculator, blank scratch paper, and pen and pencil on the exam. So no books or notebooks or anything like that on the exam, no notes other than what's on the formula sheet. And also no phones or tablets as calculators. So your calculator should be something that can only be a calculator. Like for instance, a TI-83, something like that, or 89 or Inspire or Casio or HP, whatever. But as long as it's just a calculator. Um, I think that's all I have to say on the midterm exam for now. So um, again, announcement will come out with more details about things like the time, exactly what sections will be on it, and so on after I make the exam and am happy with it. But any general questions about the exam or studying for it, anything like that? But let me get my chat window up. Okay. All right. Um, yeah, I think we got through all of the administrative stuff. And the quote of the day today is actually something that I saw over the weekend on Facebook on a group that I'm in. Somebody posted this question and so it's kind of a philosophy group. And so, at first it seemed kind of silly. It was like, is this person just trolling or what? But actually there's, I think, a deeper meaning to this. So I figured I would make it the quote of the day for the first couple of days this week. And the question is, if you could teleport into the future and teach your older self anything, what would it be? And I think, I don't know, maybe for the folks who are, like 20 years old, this might not, hit home as much. But I think even, when you're in your 20s, there are some things that you may have forgotten, that you knew when you were younger. And I think that that's the interesting point here is that, it's kind of an old trope that if you could teleport into the past and teach your younger self something, what would it be? And, there's the answers tend to be either what the lottery number is or Powerball number is or something for a certain day, or the one piece of wisdom that I would have that I would tell my younger self. But I think this makes the point that there are things that as we go through life and we have life experiences, we forget some things that we knew when we were younger. So, we might have a distorted view of reality as a result of a lot of things that happen over the course of a lifetime. And sometimes it can be valuable to think back to what we knew when we were younger and think back to that perspective. So there's, folly in youth, but there's also wisdom in youth. And I thought it was just a really interesting question because at first I thought that's a silly question. Information moves forward, roughly speaking, right? But I think there's maybe more to it than that. Okay, so jumping into related rates, we have our general process where we want to maybe get some conditions on the answer, get an understanding of what's going on. We want to look at the variables for which we want the rates to be related, and we want to relate those variables algebraically. Sometimes that's fairly trivial, like in the resistor example, we're basically just given the relation right away. Sometimes it requires quite a bit of work. We differentiate to get the related rates, then we plug in constants and check the reasonability of our answer. And we had started this one last time, and I made a goofy flub with mixing up dri dt, drs dt with the coefficients of those things, which are just the numbers. And I put just the numbers in, and I put just the coefficients in instead of the actual derivatives, and got myself all befuddled. So I fixed the statement here. So one resistor, the iron resistor, has a temperature coefficient of 5 times 10 to the negative 3, which means dri dt is 5 times 10 to the negative 3 times Ri. So the rate of change of the resistance of the iron resistor per degree Celsius, per change in degree Celsius, is 5 times 10 to the negative 3 times the resistance of the iron resistor. So this coefficient is a constant of proportionality, and this factor of Ri here, or this factor of Rs here, is what I left off last time and just forgot to tack those onto the end. And similarly for DRS dt. And the whole idea here is that we have an iron resistor and a silicon resistor, and we have these in parallel. Let me draw a picture here. So we have our little voltage source. And we have, say, our iron resistor and our silicon resistor. And we have these in parallel. So when the temperature goes up, let's say, the iron resistor gets more resistive, but the silicon resistor gets less resistive. Or if the temperature goes down, vice versa. So we have kind of a natural balancing of the circuit with respect to temperature. This might engineer some stability into our circuit. And in particular, for, engineering things for, say, planes or spaceships or something like that, where there might be really big swings in temperature that they have to handle, maybe this could be a good idea, right? This is also obviously an increase in complexity, an increase in components, maybe an increase in costs. So, an engineer would look at a lot more facets than just this, but this is our kind of toy little math problem. And let me actually pop this to the next line, so that's a little bigger. And we started with what I've typed out in blue here is basically as far as we got last time. We started with me giving you the relationship for total resistance to the component resistors for a circuit with resistors in parallel. This would not be something that you would be expected to know for this course, or that you can derive reasonably, right? We saw, for instance, the two ships, one going north, one going south. That was just basic geometry. You should be able to work that out yourself. But something like this is something that you need to be given as part of the problem statement. And remember, the goal is to find the size of the iron and silicon resistors so that our total resistance of the circuit is 100 ohms, and so that dRdt is 0 at room temperature. The at room temperature doesn't really come into play. It's just that that's where the coefficients of resistivity are measured at 20 C. So this is going to be valid at 20 C. And as we get further away from 20 C, these coefficients might be less accurate. But we have this relationship between the resistances. Maybe I'll actually bold that. And we also have this relationship between the resistances just with some algebraic manipulation. This will be the easier one to differentiate. I certainly wouldn't want to differentiate this with the quotient rule and all of that. So we see that we have r to the minus 1, d by dt of that is negative r to the minus 2 times dr dt, or just r prime, and a similar result for the iron and silicon resistors, these terms on the right-hand side. And we get that r prime equals all of this stuff, just multiplying through by r squared. I think did I miss squares on that? Yeah, I missed squares when I was typing this up, so let me put those in here. I'm just not having good luck with this, with transcribing this problem. Okay. Okay, that looks better. Yep, so I have this, and I want to set this equal to 0 because that was the condition that I was interested in. So I have my one important calculus step here. Solving, we end up with this. We can divide through by, I'm trying to select it here. We can divide through by an r squared because we have a factor of r squared in each term. And then rearranging things, we get this relation. And now we need our total resistance to be 100 ohms. And our derivatives, Ri prime and Rs prime, look like this. Okay, so let's continue on from here. All right, so I have Rs over Ri squared equals, and on the right-hand side, I have negative Rs prime, or that's 7.5 times 10 to the negative 2 Rs. The negative cancels the negative from the 7.5. And then I have over Ri prime, which is 5 times 10 to the negative 3 Ri. Or this gives me, if the 10 to the negative 3 comes up top as a 10 cubed, the 10 to the negative 2 under the bottom is a 10 squared. This gives me 75 over 5, or 15 Ri over Rs. And one of my Rs over Ri. This is just not my problem this time around, I guess. One of my Rs over Ris divides out from each side, and I get Rs equals 15 Ri. So my silicon resistor has to have 15 times the resistance of my iron resistor. There we go. I tried to hit enter there, and it opened up a new window in OneNote. So my silicon resistor has to have 15 times the resistance of my iron resistor, and their total resistance has to be 100 ohms. So now I am going to use this equation, or this expression, for total resistance. I want this to be 100. And I have Ri times Rs, well, Rs is 15 Ri, divided by Ri plus Rs, so that's Ri plus 15 Ri. Or that's 15 Ri squared over 16 Ri. We lose one of our Ris, and that's 15 16ths Ri equals 100. And we finally get that Ri is 1600 divided by 15. And then Rs has to be 15 Ri. or 1600 ohms. We might be able to simplify that 1600 over 15 a little bit, but I don't think it's going to simplify too much. What can we divide out of 5 maybe, but not a 3. So we'll just leave it like that. So with these two values for these resistors, this would of course be in ohms as well. With these two values for the resistors, we should get a total resistance of the circuit of 100 ohms. And our circuit should be kind of like thermally balanced, that if the temperature increases or decreases near 20C, our total resistance of our circuit shouldn't change much. Any questions on this problem? Okay, and then back to a more like classic mathy kind of problem. Here we have two carts, cart A and B. They're connected by a rope that is a total of 39 feet long, and that rope passes over the pulley P at the top here. The point Q is on the floor, 12 feet directly below P, and it's between the carts. Cart A is being pulled away from Q at a speed of 1 foot per second. Let me put that in here. And we want to know how fast is cart B moving toward Q at the instant when cart A is 5 feet from Q. So we want to know how fast is B moving toward Q when A is 5 feet from Q. So again, I want to kind of think of this a little bit like a movie, right? If I think of A being really close to Q, its its kind of side of the length of chord is basically going straight up to P. So if the distance from A to Q is really small, say close to 0, then the distance from A to P is very close to 12. And the distance from B to P is going to be pretty long. As I pull A to the left a little bit, well, I can increase my bottom leg quite a bit without increasing the hypotenuse much. So A isn't going to pull much rope through initially, and B isn't going to move very much initially. So B's speed initially, when A is pretty close to Q, is going to be pretty slow. And then as A, even if we're pulling A at a constant rate of 1 foot per second, as A gets further away, then to move to increase the distance from A to Q by say another foot requires quite a bit more rope than we initially required. The further A is from Q, to move it say 1 foot further away, the more rope we have to add into the hypotenuse, which means the more rope we have to take away from B, which means the more quickly that B is moving. So we kind of understand what is changing here. The 12 feet is not changing, and the 1 foot per second is not changing. But the 5 here actually is changing. So we don't want to like hard code a 5 into this problem for the distance from A to Q, because that's actually what's changing over time. That's really what this 1 foot per second is changing. It's changing that distance from A to Q. We also have a distance over to cart B, and we have kind of the two lengths of our hypotenuses here. Well, I know that those together make 39 feet, but the proportion of the 39 feet that's on the left side of P versus the right side is changing over time. Okay, so let's make a diagram. So here is Q and P, A and B. And let's say the distance from A to Q, let's call that X. And I don't know, the distance from Q to B, let's call it Y. Now Q to P, if I imagine this movie, all of this stuff changing, Q to P doesn't change. The pulley always just sits exactly 12 feet above Q. Maybe I'll do it in a different color even. I can just put in 12 there for that distance. That's going to stay the same the whole time. And then maybe I have a length I'll call like L1 and a length L2 for the rope. So I know L1 plus L2 is, was it 39? Yeah. And my question is, when dx by dt is 1, dy by dt is what? That's my question, right? This is the main thing I'm looking for. And I see that pretty clearly x is related to y, but it's related through kind of L1 and L2. May also be a good math person and put a little right triangle doodad there. All right, so I know what rates I want to relate, x and y, and I have a pretty clear, at least start to an equation to relate them. L1 is going to be some function of x, L2 is some function of y. Function of x plus function of y equals 39 sounds like it relates x and y. So let's get L1 is a function of x, and then L2 is a function of y. Well, I know that x squared plus 12 squared is L1 squared, so L1 is square root of 144 plus x squared. And similarly for L2, L2 is root 144 plus y squared. I can take those along with my constraint that L1 plus L2 has to be 39, and I get this. This relates x and y, the underlying variables whose rates I want related. Having to write kind of slowly because OneNote loves to correct my 4s into 9s, and I know that if I let a 4 get corrected into a 9, I'm going to forget about it or something and end up writing a 9 and getting it wrong. So it feels to me like 4s come up way too often, but maybe that's just confirmation bias or something because my 4s get corrected by OneNote. So I'm always on the lookout for them. But okay, we have the underlying variables related. Now let's differentiate. We want to differentiate with respect to time. So I take d by dt of the left-hand side. So I get 1 over 2 root stuff times the derivative of the stuff inside with respect to t, which is going to be a 2x times x prime. I'm going a little quickly at this point because we've done chain rule for quite a while now. We've done several related rates problems. If you don't see where all this comes from, definitely add in a couple extra steps when you look back over your notes and write out the details. And similarly for our second one here, we get 1 over 2 root stuff times the derivative of this stuff with respect to t, which is d by dy of this times dy dt, or that's 2y, the 2's cancel. So it leaves me with y prime. And the derivative of the right-hand side is 0. All right, so if I solve for y prime, well, I'm going to subtract over the x stuff and then multiply by 144 plus y squared divided by y. So I think I get minus, I get a root 144 plus y squared over root 144 plus x squared, and then times x over y times x prime. Let me make sure I did that right. Going onto the right side, it's going to be a negative for the x stuff, and I have an x prime over 144, root 144 plus x squared And then I invert my y stuff so that looks good. I arrange them this way because I know that this is going to be unitless. X and Y are both measured in feet, so this is going to be unitless. This is going to be unitless. My units of Y prime look like units of X prime. My units look good. I guess I didn't really start by saying what my units ought to be, but we can see that units of Y prime are going to be units of X prime, which looks good. I also see that they're going to be opposite in sign. Does this make sense? Yeah, it does. When X gets bigger, that means I have to have more of the rope in L1, which means I have less of the rope in L2, which means Y has to get smaller. When X gets bigger, Y gets smaller, and vice versa. So that actually does make sense. I see that their rates of change are going to be opposite. For one of them to get bigger, the other one has to get smaller. For one to have a positive rate of change, the other has to have a negative rate of change. So the sign also makes sense. Now we do have to be a little bit careful when, say, answering this in WebAssign or something. How fast is cart be moving toward Q? Well, so as X gets smaller, or sorry, as Y gets smaller, B is moving toward Q. So like if dy dt was like -2, how fast is B moving toward Q? Well, B is moving toward Q at 2 feet per second. So you have to be a little bit careful how the question is phrased and how we want to answer it, um, but that's kind of at the end of the problem after we've done all the calculations, that's something to worry about there. Okay, so I've gotten my rates related. And now I would just want to plug the individual pieces in. So X prime is 1 foot per second, is positive 1 foot per second. X is getting larger at 1 foot per second, and X is 5. So X prime is +1, X is 5. I also need to figure out what is Y. All right, let's see. So how can I find Y? When X is 5, what is Y? Well, when X is 5, L1 is what? It's a 5, 12, 13 triangle. L1 is 13, which tells me L2. Remember, my connection between the two is between L1 and L2. 39 minus 13 is 26. And then this tells me that what? 144, geez, 144 plus y squared is 26 squared. So y is the square root of 26 squared minus 12 squared. Let me just jump over to the calculator, figure out what that is. So do, here we go, 26 squared minus 12 squared, or 144 on the calculator. That gives me 532. So I don't think it's a particularly nice number, but that is what y is. So y is square root of 532. Let's write that down here. And I do note that root 144 plus y squared actually does turn out to be kind of a nice number. Root 144 plus y squared is just L2, or 26. So this just ends up being 26. All right, I can plug everything in now. And I finally get y prime is negative root 144 plus y squared is 26 over, and then root 144 plus x squared, that's just the L1 value when x is 5, which is 13. So negative 26 over 13, that's that first factor. The second factor is times x over y, so times 5 over root 532, and then times x prime, which is 1. So this is what? Negative 2 times 5 is negative 10 over root 532, and I'll just pop that in the calculator really quickly to get us an idea of what that number is. And it's about negative 0.43 or so. Geez, all of these fours. And that's, of course, feet per second. So about a half of a foot per second is how fast v is moving towards q when a is moving away from q at 1 foot per second, and when a is 5 feet away from q. So like I kind of mentioned previously, um, it's quite often the case in some of these calculus problems that we have an awful lot of setup. We had to do a bunch of geometry and algebra and so on to get this relation. We had one really crucial point here where we took d by dt, where we really used calculus. And then we had a lot of geometry and arithmetic and so on the other side to get our solution. So, if you're just an expert at whatever the calculus topic is, if you're great at related rates, that's good. But if that's all that you know, then you're not going to be able to solve most of the problems, right? We have to remember all of these, tools in the toolbox from algebra, from geometry, from trig, from pre-calc, when we're tackling these related rates problems. And I think that's what makes them kind of difficult. Optimization problems, kind of the same thing. When you're doing an optimization problem in the next chapter, it's kind of the same thing, that a lot of times getting the problem set up or getting it simplified and finishing it off after the differentiation step or the calculus step, those are often non-trivial steps. And there is a crucial step where we have to take a derivative or do something with calculus in the middle there, but often that's just one step of 10 steps or something like that. And I don't want to downplay the fact that that's a crucial step, and that's the step that we're learning here, but we also need to be good at that underlying material. So if you feel like you went through 3-1, 3-2, 3-3, you're like, hey, I felt good. Even chain rule, it's like, hey, all right, I got past the chain rule, I'm good with chain rule. But you run into related rates and you're just really not getting it. If your calculus is solid, and if you understand implicit differentiation, that's kind of applying the chain rule to these ideas. If the calculus is solid, maybe take a look at, are you having trouble getting the right relationships between the variables to start with? Is your geometry or trig or something, is there something lacking there that maybe maybe you can brush up on, or maybe that you're just not thinking about, right? Maybe you just have kind of the calculus mindset right now, and you forgot, oh wait, I forgot that this is like basically two right triangles back to back, right? If we were in a geometry class, we'd be kind of actively looking for that stuff, or a trig class, we'd be actively looking for things like that. Maybe in a calculus class, you're not quite so actively looking for that. So it might not be that you forgot Pythagorean identity or something, but that you're just not actively looking for it, and kind of switching that on in your brain might make it go a little more smoothly. Any questions on related rates before we move on? Somehow lost my chat window. Oh, I think maybe when I hit escape to get rid of that, or delete or something to get rid of that window. All right. Okay, so that wraps up 3.9 related rates. So moving on to 3.10. Again, sorry for the 3.10 coming after 3.9 and not being the same as 3.1 with no zero at the end. Um, but publishers aren't mathematicians. So um, linear approximations and differentials. Kind of theoretically or philosophically speaking, this is probably one of the top, I don't know, maybe two or three ideas in Calc 1, big ideas. Uh, so what is the graphical idea of linear approximations? We've actually already touched on it a little bit, but just as kind of a reminder, if I have some big complicated nonlinear function that could be quite difficult to analyze or evaluate or work with, if I have a point of interest, say here, let's call that point A, I can look at the tangent line. Maybe I'll call this L of X. I might want to write like L subscript A of X, but I'll just kind of omit that. This is the tangent line at the point A to our function f of x. So f of x is the messy nonlinear function, full of complexity. It's kind of the real function, so to speak, but it's very complex and annoying to work with. We have the linear function here, L of x, just a straight line. In this case, it's the tangent line. It's a much simpler model to work with, but it obviously doesn't have all of the nuance of the full f of x. So I look at L of x as a model of f of x, and I say, oh, that's kind of terrible because, you know, it doesn't do a good job of modeling this stuff over here, this stuff over here. However, if I was focusing on inputs near x equals a, if I'm zooming in at x equals a, I might actually look at this and say, well, near x equals a, L of x is actually a pretty good approximation of f of x, right? Near that point of tangency. This is kind of the idea of linear approximations, is that for inputs near the point of tangency, the linear function that is the tangent line to f of x at that point of tangency is a good approximation to f of x. Now, what do we mean by specifically by it's a good approximation and when we're near x equals a? Well, that's a bit of a more nuanced discussion, and that might be something that can be discussed in maybe a numerical analysis course, or maybe even we'll see uh, some examples of that in Calc 2. So when we start looking at integrals and so on, we can get ideas of error bounds. So saying something like, if you're within this distance of a, then your error will be less than this amount for this particular function. So that's a more nuanced discussion that, is better handled in a later course, maybe a little bit in Calc 2, or maybe more properly in a course really devoted to solving analytical problems on a computer, something like numerical analysis. But my favorite professor, Dr. Layton, he would always say the world is locally linear. So that's what this means, is that if we zoom in far enough, a really curvy nonlinear function is going to look linear, and we can really leverage that idea actually quite a lot more than it might even seem like at first. So near x star, our point of tangency, our function can be approximated by a linear approximation And in some sense, the best linear approximation to choose is the tangent line. There's not a different line, a different linear approximation that is better in some sense of the word better. You know, minimizing the error as defined as some specific function related to L and F. So this is provably the best linear estimator for f of x under some certain definitions of what it means to be best, under some certain definitions of what it means for there to be an error. Okay, so what is the definition? Well, at this point, we basically know what the tangent line is. So we're just kind of taking material that we've already worked through earlier in chapter 3 or even at the end of chapter 2, and just kind of putting it into a different context. So we can say definition, the linear approximation to the graph of y equals f of x for x near a, or sometimes we just say simply the linear approximation at a is f of x is approximately equal to L of x, which is f of a plus f prime of a times x minus a. Right? Just taking our derivative, f prime of a equals limit x goes to a of f of x minus f of a over x minus a, knocking off the limit and replacing that by the phrase for x near a, and replacing our equal sign with approximate equality. If I choose a value of x near a, if I choose 2 points, one point of interest and one secondary point close together, the slope of the secant line that I get should be close to the tangent, the slope of the tangent line. That's what we're saying here. And then, of course, I can just multiply through by x minus a, add f of a to both sides, and I get exactly this. So this comes right from our derivative definition. Let's look at a few different examples. Let's find the linear approximation at a equals 1 for f of x equals x times log x. So what do I need for I have kind of what you might think of as like a recipe here. I need to know what a is, what's my point of interest, the point where I'm taking the linear approximation and that I want to stay close to as I use that linear approximation. And I also need the function evaluated there as well as its derivative evaluated there. So I need to be able to work with this nonlinear function a little bit, but only around a. I don't have to be able to work with it everywhere. Okay, so a is 1. F of 1 is 1 times log 1, but log 1 is 0, so f of 1 is just 0. And f prime of, let's do f prime of x. Well, we have a product of two functions of x, so that's 1 times log x plus x times derivative of log x is 1 over x, or that's log x plus 1. And then f prime at 1, get a little more room here. F prime at 1 is log 1 plus 1, or 0 plus 1 is 1. So f of 1 is 0, f prime of 1 is 1, a is 1, and we just plug and chug in our formula. We see that, maybe I'll write it in a different color. F of x is approximately L of x, which is, well, that's f of 1 or 0 plus f prime of 1 or 1 times x minus a, x minus 1. That all boils down to just the function x minus 1. Let me look at the linear approximation to this function g of x, a quartic, x to the fourth minus 3x plus 2 near x equals 1. So again, what do I need to know? I need to know a. Here a is 1. I need to know g of a and g prime of a. So g of 1 is 1 minus 3 plus 2 is 0. G prime of x, I did not leave myself enough room on any of these. Let me preemptively go and give myself a couple extra spaces there too. G prime of x is going to be 4x cubed minus 3, and then the plus 2 differentiates to 0. G prime of 1 is 4 minus 3, or 1. And I have that g of x is approximately L of x, which is, well, that's g of 1, or 0, plus g prime of 1, or 1, times x minus 1, x minus 1. I see I actually get the same linear approximation for these two functions. Are these the same two functions? Well, no, they're not even close. I mean, this function is defined for negative x's. This one is not defined for negative x's to start with. Very different functions, same linear approximation. If I'm dealing with the linear approximation, I lose information. That's the penalty that I pay to get to use a much simpler function in my calculations or analysis, whatever it is that I'm doing. In the third example here, I have h of x is negative e to the negative x. My point of interest is a equals 0, and I'm looking for the linear approximation here. So I have a is 0. Need to find h of 0 as negative e to the negative 0, or negative 1. What's h prime of x? Well, negative 1, that just comes out. E to the negative x differentiates to e to the negative x times negative 1. That cancels the negative 1 in front, gives me e to the negative x. And h prime of 0 is 1. So h of x is approximately L of x, which is negative 1 plus 1 times x minus a. Here a is 0. Or again, it's x minus 1. These three functions, three different functions, at even two different points of interest, happen to have the same linear approximation. Let's take a look at these on the calculator and try to see what's going on. And get the calculator started up here. And switch the screen share. Okay, so let me first graph my linear approximation, just simply x minus 1. Then I'll graph f, x times log x. So x times, and then down here next to the number 4 button is ln x. Maybe let's just look at these two for right now. I know that I'm interested, when I'm doing linear approximations, I'm interested in inputs that are near the kind of point of tangency, near 1. So when I pick my window, let's stay pretty close to 1. Maybe we'll go from like negative 1 up to 3. So 2 units on either side. And then y min and y max. Well, I know that if I think f of x kind of looks like x minus 1, then maybe I'll just use that for my window estimation. I think it kind of looks like x minus 1, so negative 1 minus 1 is negative 2. And 3 minus 1 is, 3 minus 1 is 2. And let's get a graph of this. So there's my linear approximation, and there is my function. And I see, maybe from something like, say, 0.5 up to a little under 1.5, I mean, the graphs are almost on top of one another. If I wanted to zoom in a little further, I could maybe pick an x-min of, say, well, let's just do an x-min of 0 and an x-max of 2. So going 1 unit on either side. And again, we use x minus 1 as our proxy for getting our y's off of our x's. So 0 minus 1 is -1. 2 minus 1 is +1. So we get an even more zoomed in picture. This is going from 0 to 1 to 2. And we see at 1, of course, they meet perfectly. That's the point of tangency. But, down to maybe a half or 3/4 or so, the graphs are almost on top of one another, and up to maybe 1 1/4, 1 1/2, something like that, they're still almost on top of one another. Now, of course, as I get, say, over further to the left, or of course, even into the negative side of things, they start to look very different from one another. When we come down and turn off this y2 function, just by selecting the equal sign and hitting enter, so it's not bolded anymore, won't graph that one now. And let's type in our quartic. So we have x to the 4th power minus 3x plus 2. And let's basically just do the same thing. We'll just use the same window because that window should, that window is based on x minus 1, and this function should still be close to x minus 1 near x equals 1. It's the same point of tangency as well, importantly. This function actually doesn't look as nice as the x log x, right? It kind of comes down and pretty steeply steers back away from this point of tangency. This is again going from 0 to 1 to 2. I mean, it kind of looks like maybe, even as high as like 0.8 or so, 0.9 over here, we already see a pretty decent separation between the two functions, and maybe up to 1.1 or 1.2, we already have a decent separation. The x to the 4th function is just kind of curvier. It makes a sharper U-turn there than the log x did, so it doesn't stay as close to that straight line for as long. We can turn this one off and then graph the third one, -e to the negative x. So I do negative, and if I do second ln, the button next to 4, that gives me the exponential function -e to the power -x. And I might be tempted to just graph here and say, oh, it's the same linear approximation, but remember that the point of tangency is actually different here. The point of tangency for this function was a equals 0. So we better go and change our window. Maybe we'll go something like -1 to +1 on the x-axis, and then we'll go like -2 to 0 on y, because again, we're just kind of using this linear approximation x minus 1 to dial in our window. We can change it if we need to. And we see this one is kind of moderately well behaved. It seems like it maybe breaks away a little more readily than the logarithm, but not as quickly as the quartic. We could graph all all three of them on the same window along with their linear approximation. Maybe go from -1 to +2 on x, and then -2 to +1 on y. I'll go back to my y equals menu and just turn all of these on. So we see these three very different functions are kind of the same up to a linear approximation at different points of interest. So when we're working with the linear approximation, we lose a lot of information about the function, but what we gain is the ability to, much more easily analyze some aspect of the function. Okay, let's look at this example. Let's try to approximate 1 over, and it got a little cut off there, but okay, I think that fixed it. Approximate 1 over square root of 4.1 using linear approximations. So here I need to be a little creative, right? I need to look at this and say, all right, so in my mind, I have a catalog of functions that I could use. I could make this like 1 over x is the function of interest and evaluate. Well, let me actually just write this down. Geez, fours today. Fours today are just not working. I could consider f of x equals 1 over x and try to evaluate f of square root of 4.1. Right? I could get a linear approximation and do something like this. But remember, when I get a linear approximation, I need to be able to compute f of a and f prime of a. I mean, if I could, if I'm looking at, say, a equals, 4 or something like that, this might be kind of messy to work with, right? So I don't know if I want to use 1 over x. I guess I could maybe use 1 over square root of x, and then I'm looking to evaluate f of 4.1. And here a equals 4. Well, that is pretty close to 4.1. So a equals 4, that's a number that's pretty close to 4.1. Again, being pretty loose here especially for a math course. Why is 4 pretty close to 4.1? Well, just because it feels like it is. 4 is pretty close to 4.1, but also importantly, I can evaluate f of 4, right? It's a little hard for me to say, what should a be that's close to square root of 4.1, and also that I can evaluate 1 over that number. But it's a little easier for me to look at this perspective. So deciding which f to use and which a to use, I mean, technically speaking, it's not completely obvious. You could use lots of f's and lots of a's, but this feels like a pretty good compromise. So I think I probably won't go with this one, even though the function might be a little easier to differentiate. I'll stick with this one here. It's not much harder to differentiate, but it's much easier to plug things in. So what's f prime of x? Well, this is just x to the negative 1/2 power. So f prime of x is negative 1/2 x to the negative 3/2. And here I want f of 4.1. And what can I say that this is? This is approximately L of 4.1, which is like f of 4 plus f prime of 4 times 4.1 minus 4. All right, so what is my goal here? Again, just to recap, my goal is to approximate 1 over square root of 4.1 using a linear approximation. So my goal is to find f of 4.1, where f of x is 1 over square root of x. So that's the exact answer. But I can't really compute that exactly. So I can say that f of 4.1 is approximately, let me switch colors here, L of 4.1 but my linear approximation is f at the point of interest. Here I'm choosing a to be 4. 4 is close to 4.1. And I can evaluate f of 4 easily, as well as probably f prime of 4, right? F prime of 4 I can evaluate easily as well. So I see that these are the two pieces I need, f of 4 and f prime of 4. F of 4 is 1 over square root of 4, or 1/2. If I just kind of ask you 1 over square root of 4.1, what do you think it's about? Most people would probably say a half. Most people who are pretty math literate. They'd say, 4.1 is pretty close to 4. Square root of 4 is 2. It's on the bottom, so 1/2. That's like a 0th order approximation. We took uh, 0 derivatives in a sense. If we want a linear approximation, we can go a step further and add on the information from the first derivative. We can add on a linear term in x to the first power term. F prime of 4 is negative 1/2 times 4 to the negative 3/2. That's 1 over square root of 4 cubed. Or that's negative 1 over square root of 4 is 2. 2 cubed is 8 times 2 is 16. So f of 4.1 is approximately L of 4.1, which is 1/2 plus f prime of 4, or minus 1/16 times 4.1 minus 4 is 1/10. So that's 1/2 minus 1 over 160. If I want kind of a rough idea of how good my estimate is, I can look at this kind of linear term here. This linear term 1 over 160 is quite small relative to the previous term of 1/2. That's not a big correction, right? So going from kind of a very naive guess of 1/2 to something that's a little more technically savvy, a linear approximation, didn't really get me much correction, right? I went from 80 over 160 to 79 over 160. I changed by something in the ballpark of a relative difference of 1%. I got 1% more accurate by being quite a bit more tech savvy. This is probably a pretty good approximation. Now that's pretty, pretty heuristic. That's pretty, gut feeling-y, especially for a math course, but this is also somewhat more practical, right? So 1/2 minus 1 over 160 is 79 over 160. If we actually do square root of 1 over square root of 4.1, we get this, and what is 79 over 160? Pretty good, right? If we had done 1 over square root of 4 and estimated it as 1/2, we probably would have also been pretty happy with that. 0.5 versus 0.49, we have an error in the second decimal place. Here we get out to the third-ish, I suppose, decimal place before we see an error. So we get one more decimal place of accuracy for our tech savviness, I suppose. So I could make an estimate of 1/2 using what we might call a 0th order estimate. In other words, just approximating our function by a constant function. We could use a first order approximation. Let me redraw that constant function. Let me say that maybe this is my point of interest. I want to make it clear that the way I drew it, it was a tangent line as well. I want to make it clear that that's not a tangent line. not necessarily anyway. I could use a first order, a linear equation that has both a height as well as a slope. Or I could use another function. I could use something like, say, a quadratic function that might be able to match a little bit of the curve of our underlying function as well. Might be able to stay a little bit closer for a little bit longer, so to speak. And at the end of Calc 2, one of the big ideas in Calc 2 is the idea of Taylor series, that we can do a lot with this idea. We're going to build up to quadratic approximations, but we can really take this quite a ways further with Taylor series. So our answer, just to be clear, we got our answer here. Our answer 79 over 160. It wasn't far away from what we would have gotten with a naive answer, but it was a little better. We got another, say, decimal place or so of accuracy out of it. Let's look at another example. Let's approximate the number e using linear and quadratic approximations. So I note that e is just e to the first power. And probably the best way to get e, or e to the first power, is to look at the function that's the exponential function, f of x equals e to the x, and evaluate that at 1. So f of 1 equals e. F of 1 is what I want. The problem is that if I evaluate e to the x at 1, I just get e, and I don't know what that number is. So the place that I want to evaluate f, I don't have good information there. However, at 0, I have good information there. Anything to the 0 is 1. That's an easy number to input. And let's suppose that 0 is close enough to 1 for us to be happy. Again, is 0 near 1? Is it close enough to 1 for for our needs? Well, who really knows? That's a larger question than we're dealing with here, but we're going to suppose that it is. So I could say that e, which is f of 1, I could say that that's approximately a 0th order approximation. Maybe I'll call that like z of 1, which is just f of 0, which is 1. Here, our 0th order approximation z of x is just f of a. It's just the function output at a. It doesn't care about the input at all. So here I have e is approximately 1 for my 0th order approximation. I could probably do a bit better than that. I could use a linear approximation. I could say that e is f of 1, and that's approximately L of 1, the linear approximation at 1. Well, that's f of 0 plus f prime of 0 times 1 minus 0. So here I'm taking a to be 0 in all of these, just to be very clear about that. Well, f of 0 is 1. F of x is e to the x, but f prime of x is e to the x as well. So f prime of 0 is also e to the 0 or 1. Or 2. So e is approximately 2 is my first order approximation. What if I wanted to go even further with this? Well, maybe what I would say is, let's take a little aside here. I'm going to switch colors for this little aside. Maybe I want a quadratic approximation that looks like, and I want to use a, so I'll say like bx squared plus cx plus d. I want to model with a quadratic function. If I differentiate, well, if I evaluate, um, let me back up one step here. X minus a squared plus c x minus a plus d. We'll just put these in from the beginning. I was gonna do the work and then change variables, but I think it's gonna be clear just doing it like this. So I want some quadratic function. I want to find out what should b, c, and d be to make these match up nicely. So on one hand, I want to match the function value at a, but that's b times 0 plus c times 0 plus d. So d should just be f of a. I also want to match the derivative at a. Well, what is this? 2b x minus a plus c, and then the minus ac plus d all differentiates off. I want to match the derivative exactly at a. I want my approximation to have the same derivative as f at the point a. That's 2b times 0 plus c. So c has to be f prime of a. We've got our same answers from the linear approximation so far. The interesting question is, what should b be? What should our coefficient of x squared be? That's what we're working up to here. I want my second derivatives to also match. Imposing a linear approximation means I've matched my function value and the derivative at that point between the approximation and the function itself. A quadratic approximation gives me another degree of freedom. I can use that to match another derivative. I can differentiate q prime of x to get q double prime of x, which is just 2b, 2 times b. And then at a, I see I want 2 times b to be f double prime of a, or I want b to be 1/2 f double prime of a. So for a quadratic approximation, my linear component is still f prime of a. Sorry, my linear coefficient is still f prime of a. That was what c was. My constant term is still f of a. But my quadratic coefficient is going to be f double prime of a, not just by itself, but over 2. So I could zoom out just a touch here. I could go a step further and approximate e, which is f of 1. I could approximate it as using the quadratic approximation evaluated at 1. Which, what is it? It is f double prime of 1 over, sorry, f double prime of 0 over 2 times 1 minus 0 squared plus f prime of 0, no divided by, times 1 minus 0 plus f of 0. But nicely enough, with the exponential function e to the x, all the derivatives are the same. This tells me this is 1/2 times 1 squared plus, that's 1, that's 1, that's 1, plus 1 times 1 plus 1, or 2.5. And I could keep going with this. I could use a cubic approximation or a quartic or a quintic function, building my way up. and getting an approximation around 0 that gets closer and closer to the actual value of f at 1. So as an exercise, we're running out of time, so I'll leave it as an exercise. But we'll say exercise. Compute the quadratic approximation for each of these and investigate it. We saw the linear approximations were all the same. Are the quadratic approximations also all the same? For each of these functions, graph the function, its linear approximation and its quadratic approximation, and see how much better the quadratic approximation looks for that function than the linear approximation. Does it stay really close to the function for a much wider swath of the real line, or does it, break away pretty much as quickly as the linear approximation did? Which one looks better? The quadratic approximation should definitely look better. Does it look a whole lot better? Does it look a little better? So investigate the quadratic approximation for these three. And we have a list here of some common linear approximations near x equals 0. So for instance, something like this, 1 plus x to the k is approximately 1 plus kx, where we have a small rate and time, a small x and a small k. So this just kind of put into an application. This says that for short investment horizons and for small interest rates, compound interest and simple interest are, say, about the same. Or another application of this is with k equals -1. 1 over 1 plus x is approximately 1 minus x. Or discount rate is about equivalent to just subtracting the rate for small rates. So for things like real rate of return, you just take your investment return minus the inflation rate is a good approximation. Or maybe you should do something, maybe there should be a 1 over 1 plus inflation rate there instead, but it turns out that this is usually good enough when inflation is pretty manageable. When inflation is much larger, this holds for small rates. When inflation is a large rate, then this starts to break down a little bit. Log 1 plus x is approximately just x. I don't know why these x's at the end here lost their math font, but there we go. Sine x is approximately x, a very commonly used one, and cos x is approximately 1 for values of x near 0, also pretty commonly used. Any questions on linear approximations? Okay, so moving on to differentials then. Differentials and linear approximations are really almost exactly the same idea, just slightly different notation and terminology. So the graphical idea is pretty similar. So say we have a point of interest here. And if I go over a little bit, that indicates a second point in this function. Here I go up to get to that point. So I go over a distance, say delta x. That leads me to go up a distance delta y. And I know that, let me cheat here a little bit, pretend this is a tangent line. I know that I'm just having a lot of trouble getting OneNote to respond well today. I try not to make it go perfectly through there, but OneNote's being a little bit glitchy, but that means that like it'll miss my pen stroke for just a fraction of a second and then make it jump a little bit. So I could have a tangent line like this. Say my function went a little more like that. And I see that I can estimate the new height differential based on my tangent line instead of evaluating my actual function at the 2 points. So delta y is actually equal to f of x plus delta x minus f of x. But I know that if I take both sides and then divide by delta x, if delta x is small, I get f prime of a is approximately equal to, well, what? So this would be f prime of a is approximately equal to um, delta y over delta x. And then I see that delta y is approximately f prime of a delta x. I'm going to try to not close OneNote in the last couple minutes here, but let me actually close this and reopen it because it's being really glitchy and hard to write. So as much as I love OneNote, like 99% of the time, sometimes it's frustrating. Oh, that is the wrong notebook. That is also the wrong notebook. There we go. I probably should experiment with just making a couple different notebooks so there's not as much writing on one page near the end of the class. I should try that. Um, okay, it seems like it's a little more responsive now than it was. All right. I was trying to make it through the end of the last 15 minutes or so, but it was getting a little unmanageable. So, okay, so what is delta y actually? It's the change in height between these actual 2 points on F. It's f of x plus delta x minus f of x. If we divide both sides by delta x, we see that for delta x small, this right-hand side is approximately the derivative. So we approximately have f prime of a equals delta y over delta x. Or in other words, delta y, the change in height, is approximately the derivative at that point times the change in horizontal distance. So if I want to take one step to the right, I can estimate my change in vertical direction by taking f prime of a times the size of the step I took to the right. So we see that horizontal deviation and vertical deviation are linked to one another approximately through the derivative at that point. If we let x go to 0, let delta x go to 0. There we go. If we let delta x go to 0, so we take these 2 points and shrink them down, we take the second point and move it closer to the point of interest, we can write that notion as dy equals f prime of x dx. This is pretty clearly visually related to f prime of x equals dy dx. We have to be a little careful here, though. We didn't just take these two notations for the derivative and multiply through by dx. We didn't do times dx and times dx. We did not do that process. This is a different process. Now, of course, the underlying mechanism of this process is closely related to this idea of multiplying by dx. But what we did was we multiplied by delta x and then took a limit. It's a nuanced detail. In many problems, it doesn't really matter. You can kind of pretend that you multiplied by dx on both sides and it kind of works out okay. In some problems, it does matter. In some problems, if you kind of pretend that you multiply both sides by some differential thing, it won't work out the right way. So here it works out okay. In a lot of places it will, but we do want to be careful with the details. We didn't actually multiply both sides of f prime of x equals dy dx by dx and then just like divide out on the right-hand side. We didn't do that. We really took a more geometric approach, we did all of the multiplication stuff up here in the algebra side of things, and then we took a limit to get our differential notation here. So a little side note, note that f of a plus delta x is approximately L of, I missed a bunch of deltas here. What's my issue with this? That's approximately L of delta x. Right, my linear approximation is, oh, I also missed an A. And for some reason, I'm just having all kinds of tech issues today. My math type decided to stop math typing for several of these for some reason, and there's my a plus delta x. F of a plus delta x approximately L of a plus delta x, which is f of a plus f prime of a times a plus delta x minus a, and these go away, giving me the delta x. Okay, so that's the tie to linear approximations, is that we see f of a plus delta x can be approximated by the linear approximation, which is f of a plus f prime of a times x minus a. And the thing we're inputting in for x is a plus delta x. So there's my x coming from over here. And I have a plus delta x minus a gives me just delta x. But I also noticed that f prime of a delta x, I can just think of that as delta y. So f of a plus delta x is approximately equal to f of a plus delta y. Or in other words, if I step to the right delta x units, my vertical distance, my height, changes by approximately f prime of a times delta x units. So delta x passes to delta y just through this multiplicative constant f prime of a, and that's approximately. Okay, let's look at, and well, we have two examples here. Let's go through this first example. I think we can make it through this one in 5 minutes or so. I don't know. I feel like I'm tempting fate with as many issues as my tech is having at the moment. Is there anything I can close down? Not really. Okay. So let's consider a flow through a tube. Our volumetric flow is proportional to the fourth power of the radius. So f of r is cr to the fourth. And our question is, what is the percent increase in flow for an I% increase in radius? So we kind of have like a radius that we start with. And then let's call maybe r tilde that radius increased by I%. Or let's just say I proportion, r times 1 plus I. Okay, so that is our new radius. And our question is, what is f tilde? Well, I noticed that r tilde, r times 1 plus I, is r plus IR, or it's like r plus delta r. So delta r, the change in the input to the function f of r, is IR. So my new f tilde, well, that's f of r plus delta r, right? But that's approximately f of r plus, well, what would this be? This would be like delta f, the change in the height or the change in the output. And what is delta big F? It's big F prime of r times delta r. So I'm linking the change in the output back to the change in the input. And to do that, I need to find f prime of r. So big F prime of r is 4c r cubed, and delta r is IR. So delta F is going to be what? 4IC r to the fourth. But we note that F was CR to the fourth. So this is just F plus, well, CR to the fourth plus 4I F. Or our new volumetric flow is approximately F times 1 plus 4I. So if we increase our radius by I%, we increase our volumetric flow by approximately 4I%. Increase the radius by 10%, we get about 40% more flow. Increase the radius by 20%, we get about 80% more flow. This approximation is good for I small. How small does I have to be for it to be good enough that we're happy? Well, again, that's a more complicated question, but 10% I think is probably going to be small enough for most people to be happy, maybe even 20%. I wouldn't want to start saying if I increase the radius by 100% or 200%, that's probably, that just feels like it's not going to be a good approximation. But is 30 or 40% increase small? Who knows? Then we have to start digging into the details a little more. That's something that's outside the scope of this course. All right, when we come back, we will look at this last example in linear approximations, the differentials. Again, remember that I'm hoping that it's done whatever processing by now. The hyperbolic functions makeup video will be posted either like basically right now or hopefully this afternoon. And then next time we will start into chapter 4. So that's that wraps up our discussion for today. I'll stop the recording.